Okay, so welcome back to this video in which we are trying to work out how this random variable xt, which ascribes to each outcome the number of emails which arrive in that interval 0t, how it's going to be distributed, i.e. what's its probability mass function. And basically this is the way we're going to work it out. We're going to imagine defining some new random variables basically on here. So what do I want to start with? I'll start with the random variable y1 basically, and the way y1 is going to work is we're going to dissect up this interval 0 to t, but y1 is just going to dissect it into one piece. So it's going to dissect it into a single piece basically, like that. So it's going to keep it as the whole interval, and it's going to ascribe you a zero. It's going to ascribe you a 0 if there is at least one email that arrives within this interval 0 to t, and it's going to ascribe you a 0 if no emails arrive within 0 to t, and it's going to ascribe you a 1 if at least one email arrives in 0 to t basically. Then we're going to go on, and we're going to continue writing new random variables. We're going to write a new random variable which is going to be y2, and y2 is going to dissect this interval into two equal pieces like so. So it's going to split it up along t divided by 2, and it's going to split this into two pieces, and it's going to ascribe you basically, what we're going to do, what these are going to be, they're going to be binomially distributed. We want them to be binomial, and it's going to define success as being there are emails within this interval here and emails within this interval here. So basically, these are the trials, and success is that there's an email within that interval, and non-success is that there are no emails in this interval. So basically what it's going to do is it's going to ascribe you the number of successes. So basically you go along each of the two intervals, and if this interval is a success, then it has an email in it. If it's not a success, then you ascribe it a 0. In this case, both of these are successes because they have emails in them. So it's going to ascribe you the number of successes. So in this case, the total possibilities are that it can ascribe you 0, which is the case that there are no emails in the first that there are no successes, which means that that the first interval was a failure and the second interval was a failure, i.e. there were no emails in either of the intervals. Then it can ascribe you a 1, which is the case that one of the intervals was a success and one of them was a failure, i.e. one of the intervals had emails in and the other interval didn't have emails in. And then finally it can ascribe you 2, which is the case where both of them are successes, i.e. both of them have emails in. And I want to stress that success is just that it contains one or more emails. I do not care whether you have more than one email in here. I just care that you have at least one email in there. So success is that you have at least one email in you. Failure is that you have no emails in you. So these two, and this random variable is the same basically, but it's only one interval. And basically we've defined failure to be that there are no emails in that interval, and success to be that there is at least one email in that interval. Okay. Then we can think about defining y3, and what y3 is going to do, you can hopefully guess. We're now going to dissect this up into 3 pieces, so t divided by 3 now, t divided by 3 times 2, so 2/3. So now we're dividing up with this green strips here, so we divide it into 3 pieces, and now we look at each of those 3 portions of the interval. Ask for the first one, we ask for the first interval, is there at least one email in, or is there not? If there is no email, then that's a failure for that interval. If there is an email, then it's a success for that interval. So we say so we say, is this a success or a failure? If it's a success, we give it a 1. Then we move on to the next one. We ask, is it a success or a failure? And we add up how many successes we have. So each of them, so y3 basically, what it's going to do is it's going to ascribe each outcome the number of successes, number of successful intervals, if you like, successful intervals out of the 3 that you've made, out of the 3. The 3, okay? and it's basically going. It can ascribe you values ranging from 0 to 3 because all of them could be failures. 1 could be a success and the other 2 could be failures. 2 could be successes and 1 could be failure, and all 3 could be successes. So gradually, what you're going to do is you're going to continue on. Basically, you're going to define yn, which will map you onto numbers ranging from 0, 1, 2, all the way up to n, and yn is going to ascribe to each outcome the number of successful intervals out of n intervals. So it's going to dissect up this interval into n equal size pieces, basically. So it's going to start with t divided by n, then you'll go to t over n times 2, t over n times 3. So it's going to ascribe to each outcome the number of successful intervals out of the n. Successful intervals out of the n. And basically we've set up these random variables so that they are going to be binomially distributed. What we need to know now is what is the probability that you're going to end up with a 0 or a 1, basically. And it becomes more difficult to work out for these ones here because basically the probability of you getting a 0 is going to be 0 under this random variable, because look at the number of these that we have here. We have uncountably infinitely many of successes for this first one, and we have only 1 in the entire probability space is going to be mapped onto 0. All the rest of them, I mean, just the outcomes which have 1 email, there's uncountably infinitely many of those because it can be in any of the possible positions between 0 and t. So this one becomes very difficult to do. So really, we have to. The expected number that we're expecting to get of emails is lambda over t. So this only becomes, these random variables only become vaguely sensible once we start dissecting up this interval into enough pieces, basically, such that the probability of an email actually being in one of these intervals becomes something that isn't 1, basically. So we need the probability that you're within each one of these intervals to be under n. So if we are expecting lambda of t intervals within the entire... Sorry, I'll draw another picture down here. If we are expecting between time 0 and time t, if we are expecting lambda times t emails, then what's the probability basically going to be that you get an email within the interval t divided by, and I'll say t divided by n. So we're talking about this random variable yn now. So we've dissected up this interval into n pieces, and we've now got smaller intervals of size 1 over, t over n now. Okay, and we want to know what is the probability that you will get an email within there, and it's basically going to be lambda divided by t over n. So if you're expecting to get lambda times t in emails in the whole interval, then in t over n of that interval, and we're assuming of course that you're uniformly likely to get the emails anywhere, then your probability of getting an email is lambda over t times t divided by n. So what we find is that this random variable yn becomes binomially distributed with n trials and probability lambda times t over n, basically, is what we find. As we may, and that's for an arbitrary random variable here. Now the key thing is that this lambda over t divided by n, that needs to be a probability, so it needs to be less than 1. So you need to pick n. This only becomes vaguely sensible if you make n big enough such that this is a number less than 1. So for instance, if lambda t is 45, as we saw earlier, you're going to have to dissect this up into 46 pieces for it to become vaguely sensible. Otherwise it's just not going to be interesting. The problem basically that you end up with is just like in this case, it's just 0. The probability that you actually get that this random variable y1 is going to map you onto 0 is 0, because there's only one outcome in this entire probability space that will be mapped onto that, versus an uncountably infinite many that are going to be mapped onto the 1. And it's basically the same thing happens for these other ones if you don't pick this n sensibly. Okay, so that's just a warning about starting basically from an n that is big enough to make lambda over t divided by n less than 1, to make this actually binomially distributed. Now, is this a good model basically? Is this probability space here, is this a good model for our random variable xt? This is basically going to add up. It adds up, remember, the number of successes, and that tells you the number of intervals out of the n intervals it's divided you up into. How many of them have emails in them? Is that going to be a good model for the total number of emails you receive? Well, initially, no, because this only notes whether there are emails within an interval. It does not count how many emails are within the interval. It just says, okay, if there's a greater than or equal to 1 email in this 1 over n sized interval, I will add 1 onto this total basically. What if there are 2 emails in that interval? It still just adds on 1 for both of those intervals. However, if n gets very, 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 very big, if we allow n to get bigger and bigger and bigger and bigger, then the probability that you get 2 emails within a 1 over n sized interval is going to get very, very low. So that problem is going to go away, and this is going to become a better and better approximation for that, because it will basically add on 1 every time you get a success within an interval of size 1 over n. And if we make n very, 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 very large, then this interval will get very, very small. So really, when you get a success in there, it's probably only going to be 1 email in there. It's unlikely that it's going to be more than 1 email in there. So this is going to start looking more and more like counting up the number of emails you get, rather than counting up the number of successes you get, because successes are going to converge on being just emails, because it's unlikely that you're going to have 2 emails within smaller and smaller intervals. Or more than 2 emails, in fact. So, basically, if we let this random variable, if we let n converge on infinity, then yn basically converges on xt, and that's the intuition, that as n gets very, very large, these intervals get very, very low, and very, very small rather, and the success, and it's going to count up the number of successes. But when the emails are when the intervals are very, very small, it's likely, it becomes more and more likely that a success is just 1 email basically. So it becomes more and more likely that this is going to count up the number of emails you receive rather than just the number of successes you receive. I.e., it's basically not going to miss. It's not going to. The problem with this, obviously, at the low levels, is that it's going to count 2 emails, or maybe even more emails than that, maybe as just 1 email, 1 success rather. But as you get very, very small, that problem goes away, basically. As the intervals get very, very small and the dissection becomes finer and finer, it becomes, those separate emails will be in separate intervals now and will be counted as separate successes. So this converges on being equal to this one. So what we want to do is take the limit of the probability mass function for this binomial distribution and see what it becomes, and that is hopefully going to give us the probability mass function for the probability that xt is equal to little x. So let's just recount what the probability mass function for the binomial distribution is. So the probability mass function of y little n is equal to, let's say, little x is equal to n choose little x. So this is asking what's the probability that the number of successes is going to equal little x. Well, that's n choose x times the probability of a success, lambda t over n to the power of x, times 1 minus lambda to the probability of success to the power of the number of failures you get, which is n minus x. Okay, and basically what we want to do is take the limit of this as as n approaches infinity. Now remember, this probability mass function is only defined on x is equal to 0, 1, 2, 3, 4, etc., all the way up to n. It's only defined on those numbers because that was our probability space over here. However, as n gets bigger and bigger and bigger, n is going to go out, and it's basically going to it's going to be defined for any x is a non-negative integer, basically. So what we want to do is take the limit of this probability mass function as xn approaches infinity, and that of course will work. That probability mass function will be valid on any non-negative integer, because if you give me any non-negative integer, let's say little x over here, then I can always find you some number, some point, some number that's greater than it, and then I'm going to take the limit as n approaches infinity, so I will go beyond that, basically, when I'm taking that limit. Okay, so I'm going to take the limit now of this probability mass function as n approaches infinity. So n choose x, lambda t over n to the power of x, 1 minus lambda t over n to the power of, oh dear, n minus x. So we're going to take the limit of that and see what probability mass function we get, basically. Okay, so the first thing to do is to separate out some bits here. So firstly, expand this n choose x here. So limit as n approaches infinity of n factorial we get over n minus x factorial times x factorial. And then let's expand out this thing here. We'll get lambda t to the power of x, and then we get over n to the power of x. And then what we get is 1 minus lambda t over n to the power of n, and I'm going to separate out this bit here. So I'm going to write 1 minus lambda t over n to the power of negative x. And right, now what we apply is that this is going to be equal, we apply the fact that a fact from real analysis, that the limit of a product of things like this is of a finite product like this is the product of the limits. We also apply the fact that if we have a scalar rather in this limit, then we can pull it out. Now, scalars, as far as the limit is concerned, are lambda t to the power of x, and also this x factorial, because we're taking the limit as n approaches infinity. Those play no part in this limit, so let's pull those out. We get lambda t to the power of x over x factorial. Then we get the limit as n approaches infinity of, now let's write out, let's cancel the n factorial and the n minus x. So that gives us n times n minus 1 times n minus 2 all the way down to n minus, and then it goes down to x minus 1. Okay, like that. And then obviously what you would have had next is n minus x, it's going to look confusing, but n minus x minus 1, but it's not in the same way as this is n minus x minus 1. It's without the bracket, basically, because this really, if we expanded the bracket, would be n minus x plus 1. So that one would be n minus x minus 1, but with no brackets. But all of those beyond terms were cancelled by the n minus x factorial below. Okay? Then we get, we've pulled out this lambda t to the power of x, we've pulled out the x factorial, we then get that this is over n to the power of x. So if I just write that out, it's n times n times n times n times n times n all the way up, and you do it x times, basically. And what you will notice is that there are x terms above here as well, because from here onwards you have x minus 1 terms, but then there's this first one which makes x terms. Okay, then we take that limit, we multiply it by the limit as n approaches infinity of 1 minus lambda t over n to the power of n. Okay, and we multiply that by the limit as n approaches infinity of 1 minus lambda t over n to the negative x. Right, so this limit is very, very easy. These basically, what you could do is you could imagine cancelling this n with this n, cancelling this n with this n minus 1, and what would it become? So if I write it out again, this is going to be lambda t to the power of x over x factorial here, and then what we'll end up with is the limit as n approaches infinity, and then if I write this out, the n and the n cancel, the n minus 1 with the n multiplies, cancels out to become 1 minus 1 over n, and then we get this n minus 2 cancels with another n that's below it to give us 1 minus 2 over n, and we continue in this way to go all the way down to this n minus x minus 1 cancelling with this n, and you get 1 minus x minus 1 over n. Now, as n converges on infinity, all of these bits here, 1 over n, 2 over n, all the way up to x minus 1 over n, they all converge on 0. So this just converges on being 1 times 1 times 1 times 1 times 1, x times, which is just equal to 1 here. So that limit basically just becomes 1. Okay, now we want this limit underneath. This is a very, very, very famous limit. This is the limit of the exponential, basically, of the exponential function. So this limit is going to be the exponential evaluated at negative lambda over t, because basically, a very, very famous limit is that the limit as n approaches infinity of 1 plus 1 over n to the power of n is going to be equal to e. So let me try and show you why this limit is equal to this, and we'll do that in the next video.